Hi, I'm a PhD student at University of Huddersfield. Today I will describe how to extend the robotics planning framework with the HDJ software. We propose a reasoning method to predict the cause of function failure that may occur during the lifetime of a cognitive robot in a changing environment. The reasoning process is based on using anomaly detection techniques. The framework is for refining the PDDL model by enriching the knowledge base that the task planner relies on to produce the plans. Autonomous robots in large unknown environment require systems to act deliberately. In a planning system for a dynamic world, adapting to changing situations while another knowledge gathering is a major demand for robust autonomous behavior. The plan execution strategy must account for action failure, which result from ignorance or change. Our approach is to extend a high-level planning platform to help create more robust planning system by using theory refinement techniques to develop intelligent robot behavior based on experience. Refinement will involve reasoning over action execution failure using anomaly detection techniques. The HDJ extending components refine the original domain model knowledge that is relevant to the differences extracted by the algorithm, the discrimination process algorithm, which employs a learning process to learn new values. These values will be used to update the knowledge base. This research is carried out using a real physical now robot. The HDJ Intelligent Robotic Hierarchical Architecture is inspired by previous work on robotics architectures. It consists of 3 layers embedded into an environment that enables the recording of planning and execution and experience and subsequent adaptation of knowledge. The HDJ components bottom-up process from sensors to meaningful data with top-down mechanisms such as the focus of attention, reasoning with sensors models, and planning with sensing actions. The framework we suggest extends ROS-Plan by HDJ autonomic components. ROS-Plan is a framework for carrying out task planning in ROS, linking existing ROS components to planning tools and integrating planners with the ROS system. It employs the Planning Domain Definition Language PDDL 2.1 and the POPF, a temporal metric automated planning engine, commonly used in AI planning system. The top layer is the most abstract level and traditionally contains the aspects of explicit knowledge base of the robot architecture, which are the planning and the high-level plans. The knowledge base stores the PDDL model domain file, object instances, facts, and data that are relevant to the current task. The knowledge base is designed to collect the update model of the world and continually update by the sensory data. The planning systems in ROS-Plan is permitted to query the knowledge base for information related to the planning problem, the initial state, and the goal, or to query the knowledge for environment change, update the model world that are relevant to the current task. Plans are produced as a high-level instructions. The planning system sizes these plans and keep it simple by abstracting it away from the high-level action parameters. The intermediate layer is consisting of action dispatcher and the HDJ components. Actions corresponding parameters are processed here. The action dispatcher in charge of the transition of the domain operators into domain model. In ROS-Plan, the dispatcher selects actions of the current plan or the current task and dispatch them to the lower level or to the controller to be executed. It extracts real values from the knowledge base before the action is sent to the controller. The HDJ components process the feedback that comes from the control system and implement the discrimination process algorithm to reason the cause of the action failure and then to to produce new learned values to be used to refine the action model. The last layer is the control system, where actions are transformed into the most low-level motor commands and skills to be executed. Feedback is returned here to report either the execution was success or failed. In this section, I present the outlier detection approach, our data process collection, and the description of our novel algorithm, the discrimination process algorithm. Anomaly detection refers to the problem of searching patterns in data that differs and raise suspicions about a specific problem or issue. We suppose that examining the differences between the information related to the failed action and its previous experience or previous successful execution can lead to finding out the cause of that failure. Several anomaly detection techniques exist, such as nearest neighbor, cluster-based, and classification-based, and finally machine learning techniques. Selecting the proper technique is induced by many factors. The main factors are the nature. A standard approach for anomaly detection in dataset is to create a model of a normal data and compare or test records against normality. So first we need to define normality for the given data. Because the training data represent the value of successful execution, we assume that the historical records of successful execution are the normal data in our case. The record of the failed execution is compared and tested against the normal data by extracting the anomalies values of the parameters of the action failed. The discrimination process algorithm. This algorithm represents our novel aspects of our reasoning method. The algorithm relies on the feedback coming from the control system after each execution. The control system sends feedback to the knowledge base. The feedback is either that the execution was successful or failed. In case of failed, the information of the failed execution would be tested to extract the differences. The output is a report of the extracted differences that are considered as the potential cause of the failure, which will be used to learn new success values and then to refine or to update the knowledge model. Any detected anomaly is a value that indicates parameter or piece of information that the knowledge base such as we evaluate our system by exploring its behavior within a real kitchen scenario. Here the task given to the robot is to grab and move a cup from a table to another one. The distance between the robot to the table is the main factor of our experiment. The environment is not changed for each episode, but the initial position of the robot to the table is randomly changed. The HDJ software reasons about the cause of the failure, and then refines the PDDL model based on the reasoning outcome. We test the efficiency of the HDJ system reasoning function with failed plans to identify the cause of the execution failure. The artificial intelligence and machine learning fields aim to create a human-like intelligence and cognitive functions associated with the human mind. For this reason, the evaluation of this system is a comparison of the predictions made by the robot against our or my predictions as a human predicts. The predictions are to answer the question, why has the execution failed? When execution fails to execute the given task, the robot needs to learn why it has failed. Then, to avoid any future failure, an update to the knowledge base should be made by the refinement model. We evaluate the efficiency of the HDJ software based on its predictions, which are the detected anomalies by the discrimination process algorithm. For each failed execution, we check the output report of the HDJ. If the distance is included as a potential cause of failing the execution, then we consider it has predicted successfully. Otherwise, we consider that it's failed. In the kitchen domain, the distance between the robot and the table is a free parameter that falls within a range of values. A distance rule defines this range, which is between 23 and 15 centimeters, as you can see in the graph. The precondition of the grip action is related to this rule. It is true as long as the distance to the robot meets the condition. The distance feature is the main factor of our experiment. For each episode, we change the initial position of the robot to the table. We set the robot position to the table in a way leads to failing the execution, and we intentionally set a wrong range of values in the distance rule. So instead of 23 to 15 centimeters, we set it to 27 to 15 centimeters. When execution fails, TPA extracts the differences and learns the success values, then it sends the learned value to the refinement model. For this experiment, we employ the nearest neighbor anomaly detection approach. Each attribute's value of the failed execution is compared to the distribution of alternative attributes in the training data. To evaluate the success rate of our learning system, we tested 65 failed executions. The system correctly predicted 63 causes of failure.